Okay, sorry about that. If you don't have your screen completely ready with this ladybug document camera, you have to start all over. So I apologize. So we are now going to go on to topic 17B, but I just wanted to let you know that the last problem I did on 17A, I looked because he often gives you rates and concentrations in different units. And I thought I had noticed that they were the same, but in reality, he had 1 in millimoles per decimeter cubed and 1 in moles. So just check that the answer I gave you just was off by a factor of 1,000 for the rate constant. So now we're going to talk in 17B about integrated rate laws. So if we know that the rate is a derivative, in order to find out how A changes in a finite way over time, we're going to have to integrate that law. So these are equations that you would have been given in Gen Chem because we assumed you didn't know calculus or hadn't had calculus yet. So we will look here at doing analytical, so where we actually can integrate them and get equations. And in a lab, a computer lab, we'll look at numerically integrating them. So we're going to do 0th, 1st, and 2nd. And our second order will be both when you have the same species to the second order, or if it's second order, first order, and 2 different species. So when we start out with 0th order, that means that depends on the concentration of A to the 0, which is 1. Therefore, the rate equals just a constant, doesn't change with time. So if we want to integrate this, we have to separate the variables, which we learned some about in our thermal section. So if I, let's see. Yeah. So I can take the dt and the negative sign over to the right-hand side, which just leaves me with the infinitesimal change in A on this side. So now I'm going to integrate that from A0 up to some concentration at some time. And over here, we'll just set our time as that we start our reaction at 0 so that it goes from 0 to some other time. So when you integrate this side, it's just a constant times dt, which gives you t minus t0, which is 0. And over here, you're going to get the same exact thing. You're going to get the integral of just dA is going to be A0 or A minus A0. And so that's your integrated rate law. You will find a whole table of these, table 17B.3 at the end of the chapter, so you can always compare your results. So the next one is first order. All these integrals are fairly easy. So first order, if we do the exact same thing, the rate of the reaction, how A changes with time, it's going down, so you have a negative, is equal to the rate constant times concentration of A. So if we pull all the A's over here and the T's over here, we can integrate from 0 to T. The right-hand side is going to look the same as in the last integral. Over here, we're integrating dx over x, and we remember that from our thermodynamics is natural log. So we end up with natural log of A at some time minus natural log of A0 equals minus KT. And so you remember that the ratio of x over y is equal to the difference in their natural logs. So either way you use it, sometimes this is a lot easier. So for a second order reaction, if it's second order in the same species, it's a fairly easy integral to do. So you can say, take all the A's over here, the right-hand side's the same integral. But now if you're integrating dx over x to the minus 2, you get minus 1 over x, in this case, minus 1 over A, between A0 and A. And then if we just rearrange this, we end up with this expression. And if we get rid of this negative and multiply this by negative, you end up with KRT 1 over A at some time minus 1 over A0. Second order, when it's not with respect to the same species, you need to know about the stoichiometry, because as we set this up, we'll see immediately why we're going to have a problem. So if the stoichiometry is 1 to 1, then we know, so we set up our rate law. Concentration of A changes with time. It's negative because it's a reactant. And if it's second order like this, it'll be Kr times A times B. But A and B are both changing, so we have to find a way to integrate over both of those changes. So the concentration of A is going to be what it was at the start minus some value x, and B is going to be B0 minus x. That's why the stoichiometry is important. If this was a 2 in front of the B, there'd be a 2 in front of the x. So you need the stoichiometry in order to set up a relationship between the concentration of a species at any time compared to when you started, and then the extent of reaction. So if I rearrange and solve for x, then I can see that dx dA equals -1. So if I take the derivative of x with respect to a, so I just rearrange this, you get -1, and therefore dx equals negative dA. So where you were integrating over, or where you had a derivative with respect to a, you're going to replace it with a positive derivative of x with respect to time. And then on the right-hand side, at this point, we are going to set up just the concentration of A and B in terms of x. So that allows us to integrate just over x, the extent of reaction. So we'll take the t's to the right-hand side, bring all the concentrations to this hand side, and let me just show you that in Mathematica. Okay. So yeah, so I just plugged that into Mathematica, which takes a little while. It's not a trivial integral. I set it up using the palette, so 0 to x at some time. Set it up that it's the product of those two raised to the -1. And got this out, full simplify, it looks like this. It should be able to simplify that, but it can't. But you can easily see that if you combine all of the arguments for the logs, you will end up with exactly the same expression as is in that table at the back of this topic. So let me go back to where I was. Okay, so you could integrate all sorts of crazy orders, third order with respect to the same species, or third order with respect to 3 different species, as long as you know the stoichiometry in those cases. So the only other thing in this topic is talking about a half-life. So half-life is going to have a different equation depending on what kind of reaction you have. So if you have a 0th order reaction, the half-life is when A, the concentration has changed and it's gone down to 1/2 of what you started with. So if we have a 0th order reaction, the integrated rate law is what I had on the previous slide. And now if I'm going to say A is equal to 1/2 A0, plug it in here. And then there's a negative on this side. So if I multiply through by -1, then I simply can switch these two. And now I have A0 minus 1/2 A0, which is A0 over 2. And if I bring the Kr, the rate constant, over to the left-hand side, I have an equation for the half-life of a 0th order reaction. So there are half-lives for the other reaction, the other ordered reactions in table 17b.3. So go ahead and derive the half-life for the first and second order, just for the situation where it's second order with respect to the same species, and compare those to the equations in table 17b.3. Use Mathematica or integrate, whatever you feel you want to do, but that's a good exercise. So that is all of topic 17b.